1. And then we take the 1 times the multiplicand, shift it over, and then the 0 times the multiplicand, and make sure you line these up carefully, and then we add them all up. 1 plus 0 plus 0 plus 0 is a 1. 0 plus 1, da-da-da-da-da-da-da. So you work these out. Actually, let me just go so fast. This one, we have a 1 plus 1 plus 1. Okay? Now, 1 plus 1 would be 0 with a carry. You throw 1 more in there, and it's a 1 with a carry. And then you go into this column, and remember the carry plus 0 plus 1 plus 0 plus 0 is a 0 with another carry. So there's going to be a whole series of carries going on that you have to keep track of. So finally, by the time we're done, we end up with the product at the bottom. And if you list that out as an 8-bit number, you'll end up with a 1, 0, 0, 0, 1, 1, 1, and you check that out, it's 143, which is exactly what we got when we did the longhand method. So to help you follow the procedure, I listed out 6 steps that we just took to get the final product of 143. So you can read through these just to supplement your knowledge on the solution to that figure 7-3. So now in example 7-3, we're going to perform several multiplications, 5 times 3, 45 times 3, and so on. And again, try it first of all in decimal, then you can write it out in binary, and add up the sum and so on. And we'll see later on in the chapter that multiplication is done by a series of additions and shifting. So you shift the bits over to the left each time you have a new column formed, and shifting we'll actually cover in chapter 13. And by the way, take a look at this kind of misconception, though. Over the years of teaching, I found that most errors in binary multiplication occur when students are careless in the vertical alignment of the addition columns. Now, we don't have too many columns here, but when you look at the more advanced problems, like part C and D, when we have a lot more columns, you can see that if you aren't careful in the alignment, you shift these bits one way or the other incorrectly, you definitely get the wrong answer. So check these out on your own. So make sure you try these on your own. 15 times 15 is a good one to do. Write down the binary values and do this off on your own, and then check to make sure you get that same answer, 225. So another team discussion out here is develop a method to determine the value to carry when adding columns with several ones in them, such as those encountering the 15 times 15. Now in this column, we ended up in some cases adding 1 plus 1 plus 1 plus 1. Plus before that, there was actually a carry coming in because before that we had 1 plus 1 plus 1. Actually, we had a carry before that. So let's do this 1, and then you write down the 1. 1 plus 1 is a 0 with a carry. So now that carry comes in. We got a carry plus 1 plus 1 plus 1. That's actually with 2 carries because the answer turned out to be 4. And 4 is made up of 2 and a 2. And remember, 2 would have been 0 with a carry. The other 2 would have been 0 with a carry. So that's why we ended up with 2 carries. So now in the 4th column, we got 2 carries coming in. So it's 2, 3, 4, 5, 6. That's actually, since it's an even number, that's going to be 0 with 3 carries. So now we're going to have 3 carries coming over here. 3, 4, 5, 6. That's 0 with 3 carries. And now we got 3, 4, 5. That's an odd number. So that's 1 with 2 carries. 2 carries plus the 1 is 3. That's an odd number. That's 1 with 1 carry. And then that 1 carry up right here. So that's how we got that answer. So you're going to get a series of 1s that are getting larger and larger. So you have to watch out whether it turns out to be odd or an even sum to know whether or not you put down a 1 and how many carries you have. So make sure you try these out and make sense of it. Okay, and finally in this section is division. Division uses the same procedure that we used in long division that we learned back in grade school. So, for example, when you take 3 and you divide it into 9, so it would be 9 divided by 3, right? We get 3. You multiply the 3 times the 3, you write down the 9, subtract, see if you have any remainder. In this case, 35 divided by 5, you divide 5 into that, it turns out to be 7. You write down 35, subtract, and get 0. Now, in binary, you would write this out. First of all, you write down the 3 as 1, 1, and then you write down the 9 as a 1, 0, 0, 1. And you take the 1, 1, you see where it fits. It won't go into the 1, 0, but it would go into the 1, 0, 0 one time. And then you take 1 times the 1, 1, and you write it down carefully in the right spot, and you subtract. 1, 0, 0 is really a 4. So you get 4 minus the 3 is a 1. Carry down the 1 that's left. And now you take 11 into 11, or I should say 1, 1 into 1, 1. You get a 1 with no remainder. That's the final answer, 1, 1. Check, worked out. How about 35 divided by 5 should be 7. Again, the 1, 0, 1. You see where that'll fit. It won't fit into 1, 0. It won't fit into 1, 0, 0, but it will fit into 1, 0, 0, 0, which as we know is the number 8. So you're really taking 5, dividing it into 8. It turns out to be 1. You multiply the 1 times the 101. Make sure you line things up properly. Subtract. You end up with 1, 1. Bring down a 1, and so on and so forth. So what you need to do is go through this example 7-4 carefully on your own and see if you can do this longhand binary division. And then later on the page, here's the other 2 examples, part C and part D. This will be 135 divided by 15 and 221 divided by 17. So that concludes section 7-1. Next, in 7-2, we're going to look at 2's complement representation and 2's complement math, which is another method used for addition and subtraction. So that's it for this section. Hi, this is Professor Kleitz. In the next 2 sections, I'm going to talk about 2's complement representation and the arithmetic. The most widely used method for representing binary numbers and performing arithmetic in computer systems two's complement method. With this method, both positive and negative numbers can be represented using the same format, and binary subtraction is greatly simplified. When you look at figure 7-4, I'm showing an 8-bit number and a 16-bit number. The key element is the leading or the most significant bit is always used as a sign bit. If it's a 1, the remaining bits are used to represent a negative number. If it's a 0, the remaining bits are used to represent a positive number. Same with the 16-bitter. So because the first bit is used for a sign, the range for positive numbers is going to be all zeros up through 0, 1, 1, 1, 1, 1, 1, which is actually the number 127. For negative numbers, it'll end up being 1, 1, 1, 1 to 1, 0, 0, 0, 0, 0, which is actually a -1 to a -128. And in a moment, we'll see how we got those numbers. In general, the maximum positive number will be equal to 2 to the n minus 1. The maximum negative number will be negative 2 to the n minus 1, raised to the 2 raised to the n minus 1, where n is going to be the number of bits in the number. So this will either be the 8 or the 16. Okay, so how do you make this conversion? First of all, the decimal number that you're trying to represent is a positive number. The 2's complement is just the basic true binary equivalent. So like if you said, what's a 2's complement of a plus 18? You just write it out as you would have back, as we learned back in chapter 1. This is the 16-bit and the 2-bit, right? If the decimal number is negative, the 2's complement is found by, first of all, you complement each bit in the true binary equivalent. So you would have taken this 18, flip every bit. This is called a 1's complement. And then you add 1 to the 2's complement number to get the magnitude bits. The sign bit will always have to be a 1. So if you look at example 7-5, let's say we get the number 35, a positive 35. First of all, the regular binary for that would be the 32-bit, and then the 2-bit, and the 1-bit adds up to 35. So the 2's complement is just that number as is. So in the next example, we're going to take the same number but make it negative, so negative 35. So again, true binary is 0010, 0011, as we saw before. Flip each bit, it's called the 1's complement. So now we have 1101, 1100, add 1, and when you add 1, here is our answer. That is the 2's complement for a negative 35. So table 7-3 gives a list of the 2's complement numbers from a plus 7 down through negative 8. I think you'll see what's going on when you look at this. Here's a 7, we've seen that before, right? And they'll start going down by 1 each case. So there will be 6 and 5, 4, 3, 2, 1, and 0. If you subtract 1 more, think about it, that would end up being 1111, right? So it just kind of rolls under. So that's a -1, -2, -3, -4, and so on. And if you perform those rules that we just listed before to any of these negative numbers, you'd see that they all work out this way. So now, of course, we need to be able to go the other way. When you have a 2's complement, you want to go back to decimal. So to do that, follow these steps. If the 2's complement number is positive, you can tell by the sign there, right? Just do a regular binary to decimal conversion like we did back in chapter 1. If the 2's complement number is negative, having a sign bit of 1, the decimal number will be negative, and the decimal number is found by, first of all, you complement the entire 2-bit number bit by bit, add 1 to arrive at the true binary equivalent, doing a regular binary to decimal conversion to get the decimal arithmetic value. So let's look at a few examples of doing this conversion. So in example 7-7, let's say you have this string of bits. Obviously it's a negative because you got the sign bit is turned on. So the 2's complement number is listed out here. You complement bit by bit, add 1, and when you add 1, you get this string. Here is the true binary number, and then you just do a regular conversion back to decimal, and that's a 32-bit, 2-bit, and 1-bit. That's number 35. Don't forget to put the minus sign in front of it because we have a sign bit. How about -98? So you list it out true binary, flip every bit, add 1. There's a true 2's complement number. Actually, I was doing decimal 2's complement. And then the next one, 7-9 actually is the one I was thinking. This one, we're going to convert 2's complement to decimal. So again, we got a sign bit, so the decimal result will be negative. So you write down the regular 2's complement, straight from what we had in the problem. Complement bit by bit, add 1. And here is the true binary number, which is the 64-bit, the 8, the 4, and the 2, which adds up to 78. Don't forget the minus sign. So now in section 7.3, we'll use 2's complement for doing our arithmetic operations. All 4 of the basic arithmetic functions involving positive and negative numbers can be dealt with very simply using 2's complement arithmetic. Subtraction is done by adding the 2's complement numbers. Thus, the same circuitry can be used for addition and subtraction. So there's no need to always subtract the smaller number from the larger number. We must be careful, however, not to exceed the maximum range of the 2's complement number. That would be plus 127 to minus 128 for 8-bit systems, and plus 32,000 to minus 32,000 for 16-bit systems. When adding numbers in the 2's complement, simply perform a regular binary addition. When subtracting in the 2's complement, convert the number being subtracted to a negative 2's complement number and perform a regular binary addition. For example, if you were going to do 5 minus 3, what you would actually do in a computer is say 5 plus a negative 3. The result will be a 2's complement number, and if the result is negative, the sign will be a 1. The sign will be a 1. So in the first example, I'm just going to do regular binary addition because I'm saying this 19 plus 27 are both 2's complement numbers, so we just do a regular addition, just like we did earlier in the chapter. However, when we're doing subtractions, like the number 18 minus 7, what we're going to have to do is say 18 plus minus 7. So So down in the solutions area, 18 minus 7 is the same as 18 plus or minus 7. So we just add 18 to a negative 7. So here's the 18, there's a 16-bit and a 2-bit, right? The minus 7, we already knew how to do that, and it would be 1111, 1001. We just add these together. 0 plus 1, 1 plus 0, blah, blah, all the way through. And when you look at the answer, we've got an 8, a 2, and a 1. That's 11. And sure enough, 18 minus 7 is 11. It checks out. No, but the carry out of the MSB is ignored. It will always occur for positive sums. Because after you add it, we had a carry out, because this 1 plus 1 was 0 with a carry, 0 with a carry, 0 with a carry, 0 with a carry. We had a carry out. We'll always get this for positive sums. So here's the final 8-bit answer, 11. Okay, let's try number 22 minus 13. There's 22. There's what a negative 13 looks like. Add them together, you'll end up with 8. It works. So try 118 minus 54. Do this on your own. The answers are going to be given here. And the same with 59 minus 96. This is going to end up with a negative number. So you should come up with a negative result. So try these two on your own. Okay, so now that you've completed this, do the review questions at the end of this section, because it'll drill you a little bit more, and then do the problems at the end of the chapter for 2's complement conversions and 2's complement arithmetic. Okay, that's it for these two. Hi, this is Professor Kleitz. In section 7.4 and 7.5, I want to talk about hexadecimal arithmetic and BCD arithmetic. Hexadecimal representation, what we presented back in chapter 1, is a method of representing groups of 4 bits in a single digit. Hexadecimal notation is widely adopted by manufacturers of computers and microprocessors because it simplifies the documentation and use of their equipment. Think about it, an 8-bit system would just require 2 hex digits instead of 8 individual bits, and in a 16-bit system, it would just be 4 hex digits. So let's look at some of the arithmetic involved. First, a review of hexadecimal digits and their equivalent binary and decimal. Hexadecimal, as you remember, goes 0 through 9, and then they choose letters A, B, C, D, E, F for a total of 16 possible digits. These are the 16 hexadecimal digits. And the equivalent binary is just a straight binary counter, 0, 1, 2, 3, 4.